Have you ever just looked at a picture of a volcano and really thought about the incredible power that's locked away inside? I mean, these things are responsible for some of the most dramatic events on our planet. So let's do this. Let's journey deep, deep underground together to figure out the science behind one of nature's absolute greatest spectacles.
Because when you boil it all down, that's the real question, right? What's the trigger? What turns this quiet, sleeping giant of a mountain into an unbelievable force of nature? Well, to get that answer, we've got to go deep beneath our feet.
You see, the story of every single volcanic eruption starts miles underground, in a place with heat and pressure that are almost impossible to imagine. It's basically a giant, planetary-sized pressure cooker, and it's been simmering away for thousands, sometimes even millions of years.
Now, the number one ingredient in this whole underground recipe is something called magma. And it's important to know this isn't lava. Not yet. Lava is what we call it once it hits the surface. When it's down below, it's magma, this super hot, thick, molten cocktail of rock and all sorts of dissolved gases. And you have to understand, without magma, there are no volcanoes. It's as simple as that.
So, where does all this stuff even come from? Well, it's kind of like a three-step process. First, you've got the incredible, intense heat from the Earth's core, and that's constantly warming up the layer above it, the mantle. Then, this combination of heat and just mind-boggling pressure gets so intense that solid rock actually begins to melt. And finally, because this new molten rock is lighter or less dense than the solid rock all around it, it naturally starts to rise up, pulling in these huge underground reservoirs we call magma chambers.
But here's the thing, that magma doesn't just hang out in those chambers forever. Oh no. That pressure cooker is building up a serious head of steam, and all that magma is desperately looking for a way out. This is where its journey up towards the surface begins, and honestly, it's pretty much inevitable.
Okay, now here is the absolute best way to picture the kind of pressure we're talking about. I want you to imagine a can of soda that you've just shaken up like crazy. The soda itself isn't the explosive part, right? It's all that dissolved carbon dioxide gas inside that is just dying to escape. Magma works in exactly the same way, just on a planetary scale.
And this right here is the critical moment. As that big blob of magma pushes its way up through the Earth's crust, the weight, the pressure of all the rock above it starts to decrease. And just like when you pop the tab on that soda can, that drop in pressure allows all the dissolved gases, we're talking water vapor, carbon dioxide, sulfur dioxide, to just burst out of the molten rock and form bubbles. We're talking millions and millions of bubbles, and as they all expand, the pressure inside the volcano's plumbing system just skyrockets. So you get the picture. All that pressure, it has to go somewhere. The volcano is going to erupt. But, and this is the fascinating part, how it erupts, whether it's a huge explosion or a gentle ooze, depends entirely on the magma itself, and that leads us to two very, very different kinds of volcanic fury. So what makes the difference? It all comes down to two simple things: how sticky the magma is, that's its viscosity, and how much gas is trapped inside. Think about it. If the magma is thick and sticky, kind of like peanut butter, those gas bubbles get trapped, and the pressure builds and builds to absolutely catastrophic levels. But if the magma is thin and runny, more like honey, the gas can bubble up and escape pretty easily. This one single difference is what creates two completely opposite styles of eruption.
First up, you have the explosive eruptions. This is your classic shaken soda can. The magma is so thick, so viscous, that the gas bubbles have no way to escape. The pressure just builds and builds and builds until finally the rock sealing the volcano can't take it anymore, and the whole system just blows itself apart in a violent, catastrophic explosion. We're talking ash and rock getting blasted from miles into the sky. This is exactly what happened at Mount St. Helens, and this is how you get those iconic, steep-sided volcanoes we all picture. And then, on the complete other end of the spectrum, you have the effusive eruptions. In this case, the magma is thin and runny, those gas bubbles can escape easily, kind of like opening a bottle of soda that's gone flat. There's no big pressure buildup, so instead of a massive explosion, you just get a gentle, steady spill of lava that flows across the landscape. The volcanoes out in Hawaii, like Kilauea, are famous for this style. And over millions of years, they create these huge, wide, gently sloping volcanoes called shield volcanoes.
So, okay, we've got this incredible process, right? From deep within the Earth all the way to these spectacular events on the surface. But why does any of this actually matter? What's the big picture here? Well, when you put it all together, what does it really tell us? For one, Volcanoes are basically the planet's essential pressure release valves. It's how Earth lets off steam. Every single eruption is driven by the simple physics of rising magma and expanding gas. But it's the magma's stickiness, its viscosity, that's the ultimate decider between a violent pop or a gentle spill. And this shows us something amazing. While volcanoes can be unbelievably destructive, they're also a powerful force of creation, building brand new land and enriching the soil so life can start all over again.
They are this constant, powerful reminder that the ground under our feet isn't static at all. It's a dynamic, living, breathing system. Volcanoes are literally a window into the heart of our world. And that leaves us with a pretty fascinating question to think about. As we keep studying these incredible forces, what will the next great eruption reveal about the ongoing story of our planet?